Hi, do you remember this $250,000 IBM processor that I tore down? Well, a lot of you would because I've got 500,000 views on it. It was incredibly popular. Thank you very much. So yeah, this is like $250,000 back in the day, like early 90s vintage. It's part of the IBM System 390 processor family. It's called a TCM, a thermal conduction module, and I won't go into the details of it, but as you can see inside, there's all these thermal slugs, and there's like over 100 little individual semiconductor dies on this thing, and a 63 layer job. I will include this IBM PDF down below for the thermal conduction module here. It's got all the technical details about this bad boy, the thermals, and look inside here. It's got 63 layers inside this thing. It's got over 2 million vias in it. It's got like, 80,000 connections and all sorts of absolutely amazing. So this is absolutely incredible. And it would be even today, but this was the early 90s. Absolutely fantastic. So definitely go take a look at that video. I'll link it in, up, down, below, around. I'll link it in everywhere. Go check it out because the video may not make a lot of sense until you've actually seen the details inside this thing. But anyway, in this video, I mentioned that wouldn't it be interesting to actually try and X-ray this thing, actually see if we can see inside in this 63 layer PCB and the chips inside this thing. And well, I don't have ready access to an X-ray machine, but a fellow content creator does. So this is a collaboration video with Peter from CPU Galaxy. Thank you very much, Peter. He's actually got one of these same modules and access to a kick-ass X-ray machine. So let's have a quick look at Peter's channel here because it does not get enough love. He's only got 2,500 subscribers. This is insane once you see his content. So I'll link his channel down below, and somewhere I'll link it in everywhere. So do him a solid by subscribing to this channel. If you liked this X-ray content we're going to get from Peter, definitely go subscribe. If you're into any sort of vintage CPU stuff, he's got absolutely everything. Absolutely. Look, Intel 4004 CPUs, how microchips are made, manufacturing, retro brighting, vintage overclocking and stuff like that. He's got like obscure little CRTs and things like that. Absolutely. Here's his monster CPU. Like here is his teardown of this same module, and look at this. I don't have the machining capability to do this, but he's actually machined a cutaway of this. Isn't this absolutely gorgeous? Oh, you can see the thermal slugs inside this, and he's done this for his to show his audience, but let's actually have a look at his CPU collection. Take it away, Peter.
Welcome to this video special on my channel.
Great t-shirt.
Yeah, first of all, I would like to thank you all for 1,000 subscribers.
This was his 1,000 subscriber video, and here's his collection in the background. Anyway, go watch his intro. I'll give you a sneak peek of his collection. Look at this. This is just nuts. There's his IBM TCMs. So he's got a couple of them. Look, and there's that cutaway one. Absolutely gorgeous. And like I won't show you the whole thing. His collection is just absolutely phenomenal. Look at this. He's got Intel, all the 4000 series, the 4001 through the 4004s. Unbelievable. This is just the collection is just insane, and the videos he's got on his channel are just incredible. So like tutorials and repairing stuff, how to decap chips, no, come on, 2,500 subscribers. This channel's incredible. Go and subscribe, and make sure you hit the bell icon for Peter and my channel as well, so you get notified of new uploads. So this is definitely one of those hidden gem channels you're going to want to subscribe to. So anyway, thank you very much, Peter, for the X-ray, all the X-ray stuff you're going to see now inside this and inside another chip, which is really interesting, which we'll see in a minute. So thank you very much, Peter. Let's take it away. Let's go check out the X-rays inside this bad boy. Brilliant. Right, so what we're going to be using here, I'm not sure of the exact model. I forgot to ask Peter, but it's a Xylon. I don't know how you pronounce that. It's like, this is serious bit of kit. This is like these in big industrial X-ray machines. Look at all the different models they have. I couldn't pick out the exact one, so maybe it's like an older one, or maybe it's just not here anymore. Anyway, yeah, it's one of these big bad boy X-ray machines, like for industrial X-raying, like 3-dimensional. You can like pan and tilt and like actually see inside this thing. It's not just like one X-ray from the top. Let's go check out the footage. So this is inside the X-ray door here. You can see the turntable there. So you can see the stepper motor that actually rotates the turntable. You can see up here, it looks like this rotates it in that direction, so it tilts back and forth. And then you'll see that, let's have a look. And then, yeah, you can see that's the X-ray head up there. It's got some fans on top, must get a little bit hot. So let's actually put the module, there it is. So he's taken it out of the metal case, and so it's just the ceramic module with all the pins on the bottom. So he's putting it chip up in there, and you can see how it can they can adjust the height as well. So here's the control panel for this thing. It just allows you to, you know, pan, tilt, and all that sort of stuff. It's fairly simplistic, but you need to know what you're doing with the like materials and the exposure, like in the power limits and all sorts of stuff. And here's the, there we go. So he's adjusting the power level, 142 kilovolts. 50 microamps. Whack that into your confuser and you'll know the power level. Hang on, I've got to do that. Oh, that's only 12 watts of X-ray power, but is that a lot? I don't know. All you X-ray aficionados, I assume it is. I don't know how high this thing can go though, so maybe he's doing it low. But yeah, anyway, you can do all sorts of gamma enhancing, sharpening, and all sorts of, you know, you can muck around with these sort of systems until the cows come home. But that looks like the test. So yeah, we're in high power mode, and yeah, contrast. So we've got a live image over here, so we'll see that in a sec. Okay, so here we are. We're actually, looks like it's doing this live now. As you can see, as we increase the current there, 146 kilovolts, we start to see the detail inside this thing. And here you go. You can actually see inside as it tilts like that. So it can tilt like, that looks like, I don't know, 45 degrees or something like that. So it can go either side, and then you can rotate the thing like that. That's pretty neat. Oh, and then you can adjust the table as well. So you can, yeah, so you can adjust the table, X, Y, and you can adjust the tilt and the height as well. You can see inside there, they can adjust the height of that, everything. So here's his first attempt at a zoom inside this thing. So he's just going to go to a random location, and then let's zoom this bad boy. Here we go. Let's go in. And you can see the, what looks like square pads. We can have another look inside to correlate, but look at that. You can see the vias. You can see the, you can't, curiously, this is one of the most interesting things about this. You can't see the traces, the individual traces on the 64 layers. Maybe you could if you exposed it differently or something like that, but all those bits, they're the little annulus rings on the vias go into each layer. So I guess, you know, if you extrapolated one of them at an angle, you could actually count, if it joined all 64 layers, you could actually count that. And the big circular things that we're seeing here, they're the pins. They're the pins on the bottom. So that was an attempt at 45 degrees there. And there we go. You can see it. It's tilting like that. So now we're vertical. And that's fantastic. Look at all the layers. Look at all the layers. And these black squares over here, you've seen those were the multi capacitors. I think 4 capacitors in one unit. That yeah, that were floating around that I could actually remove. I've done a video, I'll have to link that in as well, where I actually removed those just by pushing them. I didn't have to heat them up, I just pushed them. That's to do with the type of solder that they're using to do this thing. It's just, it doesn't have much strength, and you can just push the capacitors aside. So there's square blocks of the capacitors. Can we see, oh, contrast. Here we go, we're doing enhancement. Bit out of focus now. And here we go, it's got like an optical camera as well. You can see that we're actually targeting which chip we're actually targeting. So interestingly, you can't see the die. You can't, because most of this chip area is taken up with the die. So as you can see, there's supposed to be a big die in here, but the X-rays just boom, go straight through the die. So all you semiconductor physicists out there, please leave it in the comments. Why? Why can't we see the silicon? It just goes right through, right? So yeah, oh, now we're looking like deep into the like. It's so fascinating. But yeah, as I said, the most amazing thing about this is that you couldn't see the copper traces. So I find that remarkable. We can see the via contacts, I think they're the annulus rings that go around there, but please, like, I'm no expert on this stuff, and neither is Peter. I don't think he's like a physicist and can explain how X-ray machines work. He just can use it and has access to it. So, this is cool. You could imagine having one of these toys at work. You could just play with this all day. Oh my god. There'd be no end of stuff. You'd be X-raying all day. This is fantastic. But look, we can see see that text on the side? We could actually see that. That's interesting. But yeah, you can see the the square pads, which is like how IBM do their array things. So yeah, if we go back to my video here, you can actually see the looks like can we actually see the copper squares on top? But we can't see the traces. So that's interesting. And there I am moving that capacitor. I'm just, just breaking the car. I got a video on the second channel of that. It's just magic. And yes, this is all oil filled inside for heat conduction purposes. So it's got a little port on the side. You can fill the whole module up. So yeah, obviously we're seeing the square pads. This is an IBM technique. I've got an old board I've shown off in an old video. I used to have it in the background, like on my racks of IBM. This is how they did their standard PCB technology for decades. Is they had all these little squares, and you could route everything in between those. It was just a standard in-house IBM way of doing PCBs and stuff. So it looks like we can see those. So like that's what the white ones. Oh no, hang on. No, they're like all over. That's too consistent. So I don't think they're the top layer copper pads that we're seeing there. Look, it's just a consistent square grid. So that's interesting. Yeah, no, there's something else going on there. So that could be internal. So yeah, we're targeting in the middle of a chip there. And we're zooming right in. And so you can see the individual connection layers, but no traces at all, which is fascinating. And so yeah, please leave it in the comments for those who are really more experienced in this sort of field. Please let us know what you think is going on there. So what we're going to do now is go into this part. It says it's at 45 degrees, but that looks, look at the camera shot there, that looks near vertical. So I'm not sure what the deal is. But yeah, I just like, does anyone want to count? Oh, here we go. Are we tilting over? Yep. That's tilting, but the camera angle's not changing. That's interesting. What's going on there? Anyway, it looks like we're at a 45-degree angle now. And yep, yeah, you can actually see the pads. You can see the pads on the bottom of the capacitor, little array capacitor chips there. So that's interesting. So those circles there, they're definitely the pins on the bottom. You can actually see the array, the strips of them, just like we get inside the module. So yeah, you can see the pads on the bottom of the capacitors there. That's great. So anyway, yeah, there's a reason why it's not picking up the traces. Whether or not this machine would be capable of picking up the copper traces inside this thing, I'm not entirely sure. Are they too thin? They're like half-ounce copper traces or less. I'm not sure. If we go back to the document, so there's the actual alumina substrate process, the thin film process, redundant layer, metallization, lift-off, stencil builds, overcoat, final prep, flange, grind, casting, bake-in, slurry preparation. It's all this big ceramic substrate. Begins with the preparation of a ceramic slurry and thick film metal paste, ceramic slurry, alumina powder, glass powder, organic binder, plasticizer, solvents. The material engineers, that scientists and stuff at IBM that came up with all this. It's just absolutely amazing. Dimensional stability of the green sheet. I think there's some experts, previous IBM employees. In the previous video, they commented somewhere about all this sort of stuff. So check out the comments of the original video. There should be more detail there. I'm not sure if I did I pin one? Yeah, here we go. Edward. I didn't pin that. I'll pin that now. Yeah, this brings back memories. Edward worked at IBM East Fishkill in the 80s. Worked in manufacturing technology areas where the ceramic modules were created. I'm not amazed anymore at the breadth of my EEVblog audience. There's always somebody who's worked on something I've torn down or worked at that company or whatever. It's just, yeah. It's amazing. Plant employed 15,000 people and weekly production could be driven away in the back of 2 station wagons. Yeah, an unbelievable amount of engineering went into the design of these modules and the manufacturing process to make them. The ceramic green sheet material that formed each layer of the module was created by a long sheet roll process, a machine that was approximately 63 feet long. To make the custom machine was 63 feet long just to make the green sheet material that these layers are formed from. Unbelievable. I assume, each of the 63 layers is made up of this. The roll was then taken to a die machine that precisely cut the dimensions of each sheet. The sheets were precisely punched for layer-to-layer vias and then fed into screening machines that spread molybdenum paste through the mask to create the pattern on each layer. So is that why we can't... So is it a molybdenum paste instead of copper, is it? Through the mask to create the pattern. The next step, is that why we can't see it on the X-ray? The next step was a stacker that aligned and stacked each of the 63 layers so that the vias from layer to layer would align. The stack was then pressed and ready to go through the sintering process. The sintering or firing of ceramic substrates was done in huge sintering furnaces that had a hydrogen-forming gas. Each furnace was loaded by robotic arms that moved assemblies that weighed hundreds of pounds. Wow! When the process was running, the excess hydrogen gas was burned off in a stack. It looked like something from the Wizard of Oz. Occasionally there would be an air leak into one of these furnaces where the oxygen-hydrogen ratio would be just right to cause an explosion of the entire furnace, shutting it down for an internal rebuild. Oops. On the IBM production line in the 80s. The ceramic module would then go to the thin films processing section, whereas a CMP polished for flatness. Yeah, I think somebody else mentioned it was like some ridiculous flatness these things were polished for, and the multiple thin layers were deposited using technology adapted from wafer manufacturing. In the newest generation of TCMs, which presumably we've got here, because I don't think they lasted too much longer after the one we got, there were 6 layers of thin film redistribution wiring on top of the ceramic before the chips were attached. Wow, this process had to provide for corrections in lower layer yield defects. Wow, and had to achieve 100% yield over the entire substrate. There were multiple customization laser repair processes that added, subtracted single trace defects between the chip sites. Wow. I could go on, but I'm running out of steam. Maybe someone else can pick up and describe the additional complexity of the manufacturing process. Wow. Maybe I'll contact Ed. Ed, if you're watching, can we maybe get you on the Amp Hour or something like that to talk about manufacturing, working at IBM back in the day? That'd be fantastic. Please, Edward, get in contact with me. David at EEVblog.com. That'd be, thumbs up if you want to see that or hear that on the Amp Hour. That'd be great. How often do you change your processor oil? Once every 2 years or 50 billion quadrillion instructions, whichever comes first. I'll show you this bit. Watch this. You can actually see the pins extend out there. So you can see the metal pins. So that's great. But as I said, yeah, it looks like... Oh, no, sorry. I was mistaken about the capacitors. That was just, I thought there was one on the top. There's not. No, you can see that. There's only the capacitors on the bottom layer like that. I thought, yeah, you get, if you're not thinking. Marty had a hard time thinking 4th dimensionally. You got to even just think 3-dimensionally here to see what's going on. So, Yeah, oh yeah, there we go. So yeah, once again, see, he changed the settings there, and then the pins vanished. So, you know, that's really interesting. So there's lots of stuff you can do, and then he fiddles with the contrast and whatnot. So there really is an art in using these machines to, you know, get exactly what you want. But that is just brilliant. Look at that. Thank you very much, Peter. We've got, so that's it for the TCM, but we've got one more treat for you. Let's check it out. Hands up if you remember these bad boys, the Dallas Semiconductor real-time chip with the famous battery in it that was supposed to only last 10 years, but they generally lasted about 20 before they started to die. So these are classic real-time clock chips that are in like tons of old test gear and stuff like that. So, you know, if you're buying used stuff on eBay, this has got a date of 93 on it. There we go, 46 week 93. So, oh, geez, that's 27 years old. That one's, you know, it could still be going. You never know. Anyway, it's got a lithium primary battery in it, and that just powered the real-time clock. It was just embedded, potted inside this thing. So if you ever wanted to have a look inside one of these, now, thanks to Peter, where he's put it inside the X-ray machine. So let's check out the footage. And here's just an X-ray of like straight down from the top. So you can see the battery holder here. You can see the die underneath. It's great. I love it how you can just see through the battery like this. This is like brilliant. He's done brilliantly to expose this thing for this shot. Absolutely. You can see the bond wires in there. Going over. That's just fantastic. This, of course, guess what this is? Ta-da! Spoiler alert. It's a 32.768 kilohertz watch crystal. And yeah, they've just tacked that onto a couple of the pins inside. They've just soldered it. Look, you can even see like it's been wrapped around. You can see the pin has just been wrapped around a you know, part of the pin extended up into the module, and then they just wrapped you know, took an existing regular off-the-shelf through-hole watch crystal and then just wrapped the leads around like that. And you can see it even wraps around like that and then comes out like that. That is great. And they just soldered that inside. But yeah, anyway, absolutely fascinating. It looks like the battery goes directly onto these pins here, does it? And you can see the battery contacts in here. You can make out, wow, that's just a fantastic exposure. And of course, that's just the die inside. And it's just got a battery and an external crystal just embedded in the module. That's it. So that's just what a 2032 coins or 2050 or something, or 16. I don't know if a 20 fits in there, does it? Yeah, like a 16. I don't know how thick that is, but let's, we've got some video footage. Here we go. Look at that. Still can't quite make out what thickness that is, but oh, there you go. Look at the pins. This way. This seems upside down, doesn't it? Is that? That's upside down, right? The pins are sticking up. Dead bug style. There you go. That's great. And here we go. He just fades in to the watch crystal there. We can't, unfortunately, can't see the quartz inside there. There'll be like a thin sheets of quartz going inside that, but you can see certainly see the internal connection with the crystal like that. So, yeah, I don't know. Would it even be possible to use an X-ray machine to see quartz crystal? Probably not. Physicists, leave it in the comments down below. Anyway, there you go. And last video here, let's just have a zoom in. And of course, you're not going to see, we can actually see the die inside this one, where we couldn't actually see the outline of the die in the IBM processor teardown. So that's interesting. Look, I love how like the traces only appear under the crystal there, and they only appear under there. That's just like the exposure limits and stuff. So there's the individual bond wires. Check that out. You can see the bonding. Oh, isn't that great? Wow, that is terrific. No, image gets a bit noisy, doesn't it? There, oh no, there we go. No, it's come good. Oh wow. Oh, that was stunningly sharp at that point there. Wow. Is that the maximum zoom they can do? I'm not sure what the capabilities of this machine were. Peter will no doubt leave details in the comments down below. So that's great. So that's a little bonus content there. The Dallas Semiconductor real-time chip. Always wanted to see inside one of those things, but of course they're potted, so you know, impossible to get these apart. So thank you very much, Peter, for that. That's absolutely fascinating. So there you have it. That's inside an IBM processor that we looked at teardown. So I'll put the teardown video. I'll link that in. But more importantly, thank you very much for this collaboration with Peter from CPU Galaxy. So definitely do yourself a favor and go over to his channel and subscribe. The channel name, I don't know if it's got CPU Galaxy there. Can you just get bloody YouTube and their convoluted unique IDs? So most importantly, thank you very much, Peter. This has been an awesome collaboration. I love this, and he's got a unique channel you're definitely going to want to subscribe to. Let's get him well over 10k subs. Let's get him into the 5-digit range. Heck, if 500,000 people watch the previous video, if just like 1/5 of those subscribed, he'd get his YouTube Silver Award. He definitely deserves it because there's some great content there. So thank you very much, Peter. This is absolutely fantastic. YouTube/channel CPU Galaxy. It's LinkedIn. Definitely do yourself a favor and subscribe. Anyway, if you liked the video, please give it a big thumbs up. As always, discuss down below. And if you got any more details about like the stuff we're seeing here with the X-rays, if you're an expert at this sort of stuff, please definitely leave it in a comment. As always, there's a link to my EEVblog forum. You can discuss. Every single video has its own thread over there, and you can check out all my alternative platforms. I'm not just on the YouTubes. Catch you next time.